ln x, which we can differentiate. Okay? So this is a similar idea. What we are going to do over here is we do not know the limit. Okay? So we are going to say simply that y be the limit of this. So we are going to just solve the problem only be indirect way. Okay? We don't know what that is, so we are going to call it y. And if this limit exists, yeah, sometimes you know that the limit does not exist. Okay? Well, limit exists and we call it y. And then, well, we are going to face the same situation. This x power is up here, that causes a problem. So we are going to take a log. ln y equals ln limit x goes to infinity 1 plus 1 over x to the x. Here comes a real magic over here. The limit process and the natural log. As is, we apply this limit first and then take log, right? Can you switch the order so that we have a limit of x goes to infinity ln 1 plus 1 over x to the x? Yes, we can do so if this function is continuous. Yeah, natural log function is continuous. See, the graph is like this. The function is continuous. Under that continuity, well, we can switch the order of logarithm and the limit. So, the left side is the same as ln y, and the right side is limit. We are going to apply limit last, and then we are going to take a log inside first. That is a good thing because we can apply this property of log, that is a power property. X is a power, so go out over here. So limit x goes to infinity, x times ln 1 plus 1 over x. Okay? Again, left side is ln y. So what is going on here? Look at this. You multiply x and this. Well, x goes to infinity. What about ln of this? ln of 1 plus 1 over x. 1 over x goes to 0, isn't it? Because x goes to infinity. So what is ln 1? ln 1 is 0. Okay? So this one becomes infinity times 0 case, which you learned just a few minutes ago. Okay? So we are going to apply that idea. So this is indeterminate form. And what are we going to do? We are going to switch to one of those infinity over infinity case or 0 over 0 case. We are going to switch to one of those. So what is good to manipulate over here? Once you have a natural log, it is very difficult to manipulate to other forms. On the other hand, the x, what about x? X can be written as 1 over 1 over x. Isn't that true? X is the same as 1 over 1 over x. Therefore, we are going to switch this one to again ln y equals limit x goes to infinity. I'm going to put this one as 1 over x and then put this one in numerator. So ln 1 plus 1 over x is upstairs. In denominator, you are going to put 1 over x. Okay? So now, at least we created a fraction over here. See what happens. 1 over x goes to 0. Because as x goes to infinity over here, and over here this part is going to be 0, so this one also going to 0. So 0 over 0. So this time we created the indeterminate form, which is 0 over 0 form. So do you want to do? Yes, we apply the L'Hopital's rule, which is this time limit x goes to infinity. We are going to differentiate, yeah. It's kind of when things more complicated, we want to make sure that what we are doing is right, okay? So take a derivative of 1 over x and take a derivative of natural log of this. Take a derivative of both. So here we go. What is a derivative of 1 over x? I know, negative 1 over x squared. Now let's be careful. What is a derivative of natural log 1 over and 1 plus 1 over x? So we have to apply the chain rule. So ln u, when you differentiate this, the result is what? U prime over u. So u is of course 1 plus 1 over x. So are you ready? U is this, 1 plus 1 over x. So we are going to put this 1 plus 1 over x. Okay, goes to denominator. And in numerator, the derivative of u is 1 plus 1 over x. So derivative of this is the same as derivative of 1 over x, which is negative 1 over x squared. Strangely enough, that earlier we found this, but these two things cancel out. So what's left is over here. Okay? So after the big cancellation, we have limit of x goes to infinity. Here is 1 over 1 plus 1 over x. So a little part is left. Okay? So what can you do? This one is going to be 0, correct? So 1 over 1, which is just 1. So is the answer 1? Not really, because after you take a log of this limit, the answer is 1. Don't forget that, okay? We took a log. So in other words, go back, refresh your memory. This is the limit of this problem. The answer for this limit is y. But what it says over here is ln y equals 1. So what does it tell you about y? Well, that means y equals e. Okay? So what did he say over here? This limit is limit x goes to infinity. 1 plus 1 over x to the x equals e. Yes, we use e a lot, okay, for the exponential function and for the base of a natural log. But this e was created like this. The definition, you can say this is a definition of the irrational number e, that is 1 plus 1 over x to the x as x goes to infinity. Okay, so this is a very big thing. By the way, how large is this e? Well, this e is roughly 2.718. Okay, so roughly 2.7. So the limit 1 plus very, very little thing and to the infinity power, so that gives you 1 to the infinity form. The answer is e. That is very, very difficult to just guess or just to expect. Okay. By the way, it has a kind of a twin version of a definition, which is limit, this time x goes to 0. Oh, what kind of a twin is one says x goes to infinity and the other one goes x goes to 0? That is, you can say this is 1 plus x to the 1 over x. It's a completely different story, right? But what's happening over here is 1 plus x. So this is like 1. And 1 over 0, so this is like infinity. Okay, so this is kind of a dual version of the definition of e. Well, I think that you are going to see this one in the homework problem. Okay, I'm going to leave it to you. indeterminate form of 0 to 0 power. So this time evaluate limit of this sine x to the x, sine x to the x power as x goes to 0 plus. Okay, I'm sure there is a reason why it has to go to 0 plus. Okay. Well, did we see earlier something to the x? So sine x is varying and x is also varying. Therefore, in this case, we cannot do just a regular way of taking limit. So we are going to use, again, the same idea. So let's call this limit y, if it exists. Okay? Well, so after that, we are going to take a log. So we are going to take a log ln y equals ln limit of this. Here is sine x to the x power. Again, sine function that is continuous, so we can switch the order. So limit x goes to 0 plus, and then natural log come inside first. Okay, so natural log of sine x to the x power. Then, because of this natural log, this power x comes in front. Okay, so I'm going to say this power comes in front over here. X times this. So what kind of form do we have? This one goes to 0. What about here? ln sine x. Sine x, x goes to 0 plus, therefore sine also goes to 0 plus. And therefore natural log of 0 plus. What is going on here? So first, you wonder, why is not just x goes to 0? It's not good enough to be small. It says x goes to 0 plus. Yes, there is a reason. Look at this sine function graph. Sine function graph is continuous everywhere like this. As x goes to 0 plus, coming from this direction, yeah, this is, you can say, yeah, still going to positive side. On the other hand, if you put it x goes to 0 minus, it's going to coming down from here, right? Coming from this direction is going to approach 0 from the negative side. And natural log, when you have a natural log x, x has to be positive. Yeah, that makes a big difference over here. So 0 plus and 0 minus, it have very, almost no difference, okay? Almost no difference, but the domain of this natural log function that requires x is positive. Therefore, that's why this 0 plus comes in here, okay? So here we go. What is that? Natural log of 0 plus. Well, again, we look at the graph again. What do you see? 0 is here, 0 plus this side, the right side. So as the function goes down here, indefinitely, just going down indefinitely, it goes to negative infinity. Okay? So this one is what kind of form is that? Again, 0 times negative infinity. Don't be distracted by negative sign. Simply just that is the same as like a 0 times infinity case. Simply you put negative sign to the answer. Okay? So this is 0 times this. So we are going to overcome this. How? Yeah. Again, x times natural log. Natural log you cannot manipulate. So just stay put here. Instead, the x is going to change to 1 over x as before. So limit x goes to 0 plus, make it this one as 1 over x, and the natural log of sine x. So this one is going to positive infinity because I can say positive clearly because 0 plus over here, and this one goes to negative infinity. Again, don't be distracted by this negative sign. The main part is what? Infinity over infinity. Okay? So this is a legitimate indeterminate form. So what are we going to do? Yes, we are going to apply L'Hopital's rule. So here we go. I'm going up over here. So apply this limit after we differentiate top and bottom. Again, the derivative of 1 over x is negative 1 over x squared. What about here? Again, natural log. The derivative is u prime over u. This time u equals sine x. Isn't that right? Okay. So the derivative of sine x is cosine x. So cosine x over sine x. What is that? Can you call it cotangent x? Okay. So the relation over here is going to be cotangent x over here. So what is going on? Let's flip. Very acrobatic over here. Instead of looking at this, okay, it is right now what is going on. Cotangent 0. Well, cotangent, I do not have well, I know what that is, but for you, it is a lot easier to when you switch to a tangent function. So cotangent is 1 over tangent, is that right? 1 over tangent x. Here is negative 1 over x squared. So we switch the location. So negative x squared goes to top and the tangent x goes to bottom. It's easier to think than this. Alright? So this one goes to 0 and this one tangent 0 also 0. Well, this is 0 over 0 in indefinite form. Yeah, I'm sorry, not indefinite. Indeterminate form. So what can you do? Let's use L'Hopital's rule. So here we go. Limit x goes to 0 plus derivative of negative x squared is negative 2x. Derivative of tangent x is secant squared x. Okay. What do you think? Are you ready to apply L'Hopital's rule again? Not so fast, okay? Not so fast. We evaluate the situation. Well, the numerator is 0. What about denominator over here? What is secant 0, by the way? Secant 0 is reciprocal of what? 1 over, cosine 0. And the cosine 0 is 1. We know that, so this is 1. So secant 0 is 1, so secant squared also 1. Therefore, it turns out that it is 0 over 1 form, which is not indeterminate form. Okay? So we can conclude right over here. It's going to be 0. Okay. So is 0 the final answer? I don't think so, because we got 0 after we took the log. Is that right? So our original limit and the limit problem, the limit, we called it y. Okay, we just named it y, and right now ln y turns out to be earlier what? 0. So what can you tell about y? Of course, y equals 1. So in other words, this limit is 1. Okay, so, well, this is kind of, that as complicated as it can get, all right, in terms of complexity, yes. The next one is example 7. This time, it's another interesting thing. Infinity minus infinity. What do you think? Is like a 10 minus 10 is a 0, so infinity minus infinity is like a 0? Well, not really, because again, infinity, there are many different levels of infinity. So this first infinity can be really huge compared to this. So dominating factor. Or this one can be really dominating, or they are really neck and neck. We do not know what the final answer is, okay? So this time, let's see, what is the limit? Limit of, yeah, I cannot make any mistake of writing wrong thing. 1 minus, I'm going to be extremely careful, 1 over ln x minus 1 over x minus 1. So why it is infinity minus infinity case? Again, over here. ln x, ln 1 is 0. So 1 over 0, which is infinity. Correct? And what about this? X goes to 1 minus, so 1 minus 1, which is again 0. So 1 over 0, which is infinity. So infinity minus infinity, we don't know which infinity is going to the winner. Okay? So, and another thing, more practical reason is that, okay, we cannot determine the limit at once. So we want to use L'Hopital's rule. So what's wrong with that? L'Hopital's rule requires like f of x over g of x, like this. One function over another function, just one fraction. Right now we have too many fractions, 2 fractions over here. So what do you need to do naturally? Yes, you are going to combine these two together, so make it as like what? One single fraction. So let's combine them together. I know it looks strange, but limit x goes to 1 minus, and this is ln x times x minus 1. And here is x minus 1 minus this ln x. So we combined together, so we created one fraction. So now we evaluate the situation as x goes to 1 minus. Here 1 minus minus 1, 0. And ln of 1 is 0. So this is ln of 1 is 0, so 0 over. ln of 1 is 0, and 1 minus 1 is also 0. So this is what? 0 times 0. Of course that one is going to be 0. So this is an indeterminate form of 0 over 0. Okay? So this one is, we can apply L'Hopital's rule.